Okay, so before this, I was spending a lot of time just fixing the mic and everything because I was assuming that in this particular recording, I'll like talk about a lot of stuff, and so I just wanted to check if the mic will record properly. And I have two fans here, and like there was too much background noise, and I had to look into like the OBS filters. But ultimately, I just decided to like put one fan a little slower, and that seems to be a fine like temporary solution. But yeah, let's see. Anyways, so I had put a few videos where I was like doing some compiler related work. So just to introduce that, I've been working on like as a side project just for fun, like a basic systems language. I mean, even calling it a systems language is like maybe a little too professional because it's sort of a very minimal language right now. So it's kind of like a subset of C at the moment. So yeah, I'm assuming like if there's any language that is going to be a professional and like a language that is usable in any real work, then it has to be like at least at the level of C in terms of the features that it has. So, but that's okay because it's not meant to be like that. It's just a side project that I'm working on. Um, so, what I wanted to talk about was like first of all, like why I'm doing this, why I was working on it. So I might not continue. Like I had to work on a lot of random things. Like if I just go on GitHub, um, so I think like I have like many random projects. Uh, so okay, there are like some private ones that are like visible here. So I'm thinking of working on these. I've not really done much. Um, so like recently I worked on this editor, which was not again it was not a serious project. It was this one was actually just like one night where I was thinking of like I was like using Emacs and so for some reason in my Emacs like when I load files it takes like 2 seconds every time I'm loading a file, and I try to remove all the configuration and everything, and for some reason it doesn't speed up for me. And should not be like that even for Emacs, but anyways, uh, I don't have a problem with Emacs. I still use it, but I just felt like it would be an interesting idea to see like how difficult it would be to make an editor, which I had been thinking for some time. But now it's like I think much easier with like so like people like to vibe code these things like this these days, like you use Copilot or something and then you just ask it to like build something and it like it'll throw in some code. That was not my idea. Like I mean it is doable, but like I like to like know how something is being implemented, and I just like programming anyways. So but this was like more of a experiment that I wanted to try out very quickly. Which, as I said, I just spent one night on this, and so what I did was basically I just start a project, and I have like the I have a broad idea of how I want to go about it. So. Like you have a text editor, so like you want to create a window, you create a window first, and I know that like you need like windows.h and in C++ or C. I started with C, but then like there's some issue with direct write. I think like uh, like the libraries on Windows, uh, the Windows API only is like supporting C++ for some reason in direct write or something. So I had to like move it to C++, but that was okay. Uh, so I get to create a window, and then like it renders after like in a loop, and like you have different events. Then you use like stuff to like write text to the screen, You have to handle the cursor position, you have to handle like keyboard events, uh, and all of that stuff. So I would like have the code work done manually, but at the same time I was like going to ChatGPT and like saying, okay, if I want to do this particular thing, like what would be the way it is used, like what kind of methods I need to use, like in direct write or whatever, or Windows.h, because I don't know the names of the methods and all, and I think that is kind of just like it's kind of knowledge that is not, there's no logic in anything involved in it. It's like just knowing like what method is supposed to be used for what purpose. So like for that, I think it's fine to use ChatGPT and that. So I just take snippets and like I'll use them, modify them, and like once you know like this is how to do one thing, maybe you have to do something similar and you do the same thing in a like modified way. So that is how I just worked on it. So like I have like many projects like this. I keep on working on like random stuff. So this compiler is also one thing, but it started out as a very small thing and it like grew into I think a more serious project. Serious in a again uh, not a professional sense, but just personally for me. Um, so um, it's been, I think, more than half a year maybe since I've started working on this, and but I didn't like spend all of that time like working on it. I've like had times where I was not doing anything, and times where I like did something for a few days and then left it because like they were like in any development work that is like difficult. You will like get stuck at some place and then you have to like do the same thing again and again and try different things, and some stuff is just irritating. But most of the time I think I have like eventually been able to push through those issues. But yeah, anyways, so getting back to the main thing. So so to begin with, for people like who might not know, so who might not even know like what a compiler is. So basically, like we have like any software that we write, everyone knows that we have languages. This stuff like C, C++, Python, Java. Like I mean, there are many languages that people know of. Again, like there is like some nuance here, like because all languages are not just compiled in the traditional sense of it. Um, like there are like interpreted languages or scripting languages. Uh, well, technically like Python and JavaScript are scripting languages, but even there's like some variation in how it works. Like Python is compiled to some bytecode, and then that is interpreted, I think, at runtime, like in like some sort of, I don't know what it's exactly called. It's kind of like a VM kind of a notion or something. But there is some sort of compilation that does go on. It's just that it doesn't compile to like proper binary. But there is something. It's like some, I think, like there is a C Python formulation of it in which it happens something like that. Um, then JavaScript is different from that. I think it is legit compiled in the browser. I guess like in Chrome there's V8. Anyways, but like if we keep everything aside and like just keep the whole thing very simple, just like at a beginner level, I think the idea is that compiler just takes your code, which is, so what is code is, I think, a very glamorized notion. Like people look at like discolored syntax and stuff in a file. Like you just go to any file. Let's open some file. See, 2 seconds. So this whole thing. So you can see like this stuff that's like here. There's comments. There's like keywords in white and some other stuff. I have like very minimal syntax highlighting. In VS Code, it would be like very like pronounced. Um, so the data types, and so there's a lot of stuff going on, which it looks clearly very different from just a text file, which is something like this notepad file. Um, but actually, if we really take it to the basic level, this is also a text file. So for the computer, just if you have just any file which has stuff like this written, really it's just text, and the file just has like a different extension instead of .txt. But I mean, even the text even like extensions are like just a virtual concept. It's not like it is some real thing. It's just kind of like a name. It's just a different part of the name. Let's say like you have a file name, and extension is also like just a special name, but it doesn't really do anything different as such. So, how do you take this and have something that runs on the computer? Um, yeah, so like that is also like not a simple thing. So people just assume like you have code and the code runs, but that's not how it works. So um, there are layers to this, but the thing is that actually the computer understands very few basic instructions. Few is, I guess, an ambiguous term, but it's still kind of few in some way. Um, so, like the computer ultimately is like hardware, and the hardware is there some processor, and for example, like in this case, it will be the x64 processor that is for this computer. Um, there's like all kinds of other processors. Um, so they have some particular instructions. So there will be like jump instructions, some call instruction, move instruction to move data from one memory location to another. Like jumping, as I said, is like kind of a control flow equivalent, or rather, it would be like the actual base of what control flow is happening at the processor level. Um, and yeah, so like there are many instructions like that. um, so those are kind of defined in the sense that they are like physically present in the hardware, in the processor, and the processor understands those. um, but as you can see here, this is like kind of readable text. So these are not like instructions for the processor. This is like, and there's a lot of stuff going on. So like structs are there. You have like some inline. There's a data type. There's like operations, or like symbols for operations, pointers. There's like a return. Like wait, return is also like, I guess, kind of an instruction. Um, but yeah, so the idea is that we have this kind of text file, and we want to be able to convert it into a kind of a format in which the computer will actually be able to run it, because ultimately the processor needs to run it. So how do we do that? And that is basically where we get into like this concept of a compiler. So compiler is basically this thing that is going to take this file, this text file, which has something special written. Like it's not just arbitrary text. It's supposed to be like something written in a particular way, which follows some rules, where there are like certain words that mean something very specific, and there's a certain grammar. Just like in any language, like English, French, like there's like a way of saying things that actually is sensible and meaningful, which would not be the case if you just put random words together, even if those words are part of the vocabulary of that language. So, in the same sense, like if I just put this bool before the inline, it would not be the right way to do it. Just in this language, it's just the way it's done in this language. So that's like the way it is. So that's the linguistics component of what we are dealing with. So languages, just like human languages, programming languages also are kind of just a human level abstraction that makes things easier for us to work with. Uh, but we ultimately need the processor to have those instructions that actually do the thing. And that means that we need a compiler in between this text and the actual instructions that we will run. So there needs to be something that translates this to that, and that is, yeah, that's basically what a compiler is. It is something that does that. Uh, in the sense of visualizing what it is going to do, like you have a some file, and you want the compiler to produce an executable. Uh, so in like Windows, we have .exe files. So something like that you can say is what is the goal of the compiler. And then if you want to think of it as an input and output, so the file is the input, one file or multiple files, and the output would be some executable. So you just run the executable and it should run. So yeah, so that is the goal. Now, now there's a question here before we get into like how you actually start like working on something like this, and like how compilers work, and more of like how I was working on it. Um Before we go there, there's like kind of this question. Um so why would anyone make a compiler? So obviously, like this is not it's not a, let's say, a new thing. In fact, it's probably like amongst the oldest things. Not oldest, I think, but it's like pretty old of in the sense of like project ideas, let's say. Um, like we have all these languages, and like there are like so many now. I think it's like one might argue that we have too many languages. Um, So there can be the question that like what's the point of working on a compiler, also because so this is not something that is like easily monetizable or anything. It's like, so there are many languages already that are doing a lot of different things for many different purposes, uh, and it's been going on for many decades. Like the C compiler came in 1972. Dennis Ritchie worked on it at Bell Labs. Then we have like many languages since then, and like different languages do different things, and it's not even very monetizable, and it's very difficult to make a compiler. So all these are like negatives that you might think of if you're just working on a project for fun. So but ultimately, I think if I tell the most honest answer is like just I just wanted to do it. Literally, that's like the most clear answer. Like yeah, I mean, uh, like if you think it's like something that's fun to do, then why not? I guess. Um, Secondly, if you want to go like beyond that to like at some deeper level, the first thing is that I like programming, like and I'm interested in computers. So I think this is also like a discussion that it's like maybe another branch that at some time maybe I might talk about. But so in software development, like the kinds of people that you find vary a lot. Um, Many people are kind of focused on just building apps these days. Like you want to like make something like some kind of website or some mobile app or something that does something, and you have users or you will use it, and like you solve something for them, and or you provide some kind of service or a product, and it's very like result driven in some way, that like it's almost like there's more focus on the product in that and less on the technology, which is all right in one sense. I mean, if that's the interest of the person, there's nothing wrong with that. But I've always been more interested in the programming side of things, and even in programming, I've been interested, I think, in the side of the computer, because there is a human side to programming and a computer side to it. I think the human side would be like you just write code, and it's like it looks nice to write code, and it's fun to see like stuff being generated from what you write. So Python can give you that. you can write code in Python, and like you can get a lot of work done with very little code, and you'll like get the fun from like just coding and also seeing something at the end of it, like some kind of a result. Um, but the way I think of it is more on the computer side. So I like to think about what the computer is doing internally, um, because I mean at the end of the day, like programming is about the computer in some fundamental sense, because everything that we are doing is going to run on a computer. So all of this stuff that we do, which actually the compiler is about, it like takes our software, it builds it, and it converts it into some form that the computer understands and the computer runs, and which means that it runs on some hardware. Um, so at the end of the day, it's kind of about making things that work, or rather making things that the computer understands. And if you want to make things that the computer understands, and I just feel like it makes a lot of sense to think from the perspective of the computer, which is actually something that there's like what do we say, like a field, or I don't know what is the right word for it, but so low level software and low level thinking is kind of, I think, oriented in that direction. Uh, um, so yeah, I don't know. So there's something about like compilers is which is one is that they make you think at a meta level. So you go beyond just the language and you start thinking about the language from an abstract perspective of like, okay, language itself is data, and you want to translate that into something. So your language, the code that you write itself is something that you're operating on. So you start thinking of code in a very concrete and real way, and not like a human. Because we are, I think, used to these days just reading code like a person, and like it's supposed to be like Python is almost designed that way. There's problems with that approach, I think, because you start to like forget about uh, like these aspects that basically like this is meant for a computer basically. And I think like okay, that's like a huge discussion in itself, but anyways, yeah, I think if I get too much into that, that will be a discussion in itself. Like you can get into like talks about performance optimization and like those things, and like the there's like a lot of stuff about how software is doing these days, and like there's like an idea that software is kind of in decline in terms of quality, and like people like Jonathan Blow, Casey Muratori, like they have like talked about this a lot. There are like software conferences where things like this are discussed. Um, I mean, there's like all of that stuff on YouTube, and anyone can go and look into that. I think that they have said a lot more on this. Uh, but all of that begins with just like having an interest in thinking about things from the computer's perspective. Mm, and yeah, I think that just that fundamentals approach is interesting. So when you work on a compiler, I think that kind of a thing just comes up also, because a compiler produces an executable, and if you want to make a good compiler, you want the program that actually runs to be fast, uh, which would be runtime performance, runtime speed. um, so like languages like C, C++, like they're known to be fast. Even Rust is fast. Like at least like okay, uh, defining fast is also something that's kind of important, because like just saying something is fast is like, I guess, too vague. But yeah, that's like the general consensus or whatever. Mm. Um, but then there's like even stuff like compile time performance, how fast your program compiles, which is also interesting. So like there are two performance challenges that are there as part of the process of making a compiler, uh, because your compiler itself is a program, and the executable which runs, which is like the output of the compiler, you can say like that's the main goal. Like you want runtime performance. So if you build any software in this new language that you're working on, and you compile it and it doesn't run fast, that would be like the main bottleneck. I guess like you would want that to be fixed. Like, you would want something like C, C++, Rust, all these systems level languages. Like they have this like speed advantage. Uh, so you would want that. But there's also like compile time performance. So like which is also something that I think is kind of important, because like even right now, like I have a C++ program which I'm building, and it takes a lot of time to build, and a lot of time means like I guess uh, I don't know, 8 to 10 seconds or something. It's like obviously like I've not written like code that's like optimal. I guess that's like a given. But still, I think it's not such a big project at the moment. It's like probably 5,000 length. Um, and so, for example, Jonathan Blow has his language J, um, and like he has demonstrated in one talk, and I mean he has mentioned it many times as well. But so he has like a game he has made in that language, which is like 300,000 lines big, and it compiles in like 2 seconds, uh, which is pretty great actually. It's almost unimaginable in any other context. Um, when that is compile time speed. So to have software that does that is also something that's interesting. To be able to think of that also is a kind of a challenge in itself. So, like all these things just come into your mind when you start working on a big project like this, which is a compiler, and I think the last part about why you can make a compiler and why making it is useful would be like just the nature of the project itself, which is it's a compiler, and in the process of like understanding how compilers work, you kind of just learn a lot about programming itself. So because I'm interested in programming, and not just programming, also computers, because the goal obviously is like to make something that runs on a computer, and you start thinking about like assembly and instructions, and like translating like syntax trees into some kind of IR, uh, and that IR could be just LLVM IR, or like you can have some bytecode in between of your own, um, and then you have to like ultimately convert that into some assembly for some target. um, so there's that, and there's like linking and stuff, and like there's so many issues that you come across that also like I think just naturally teach you a lot of stuff. And like when you link with stuff that you have created, like something cannot might not be compatible, because then you might realize that okay, there's not just stuff like compatibility at the source code level, which is like you can say API compatibility. There's like stuff like ABI compatibility, which is like at the binary level. So when you compile code, it forms some binary, but different compilers can compile stuff differently, and if different compiling for different targets compiles things differently, and so things that are compiled differently might not be compatible with each other. Um, that's also like stuff you have to think about, which is also interesting. Um, so it's like just like that is something that you could already know, but it's like if you don't know, which I didn't know a lot of stuff before working on this. I guess I just kind of went into it with minimal knowledge, but I had like some abstract idea of like some stuff like maybe what NAST is, and um, I don't know what else. I guess I had some idea of assembly. I have not like done like serious work in assembly or anything. I've never actually even read much assembly, but I kind of knew like what instructions mean, and like I had like written a simple small project before this, which was like sort of a virtual machine it is like the idea of a Turing machine and like creating a symbol. And I would say I don't know what's like maybe an emulator for it would be the right way to put it. And like to have a assembly language for that emulator, uh, which and I'm like had it to be in a way that I could actually like write assembly programs and run it on that emulator. So that is I think the thing that I worked on before this, and that made me actually somewhat confident to actually work on a compiler because I thought that okay, like I kind of know what assembly is because I'm able to like write this project where I can run my own assembly language on this virtual machine. Look, like I mean, in retrospect, it was like almost unrelated to anything I'm doing right now in this compiler, which is like insanely much more complicated and much more involved with many other things that have nothing to do with that at all. Uh, but I think it was mostly just that motivation that I needed, maybe. Yeah. So, anyways, I think this was much longer of an overview than I thought. So, okay, let's just I think go into the main stuff. Um, so, so my idea of this discussion was to like kind of go over how I went through this project, and so the way I did it was kind of I guess I don't know how it's like done in a real way, like maybe like my idea is that most languages historically I guess have been made by people in a very solo direct manner, like one person just wanted to make a language and like this just did it. It is not like some kind of big corporation and like coming with a team to build the whole thing. It's obviously yeah the case that there are like languages that have been then iterated over and then worked on by teams, like that's like the case with not many languages I mean now. But usually they have not started out like that, and they've started out like this one person like soloing the whole thing, and like they just make something and it works and people like used it. Um, uh, so obviously there's that. Anyways, but I don't know how it's like generally done traditionally, but this is just how I did it, and I'll go over that. So okay. Um, so I guess this will mix a little bit with like what a compiler kind of does fundamentally, because like I will kind of have to go over that anyways. Um, so I think let's begin with that. To do this, I think I can open this whiteboard. Um, so even before that, okay, I mean even like we have this program here. So like we have this file. As I said, this thing is just text file, right? It's like ultimately like just characters in a file. Um, Now, the first stage of the compilation process is to make the thing. Um, so you want to break the task of like working on like this text file into some a more digestible thing. Like when we as humans read this, we can see like we have this word here, there's another word, there's a bracket, and inside is there like bunch of statements separated by commas. So this is a human intuition that is parsing this right now. Um, the computer doesn't know that, so we need to do that for it. Um, so to begin with, I think we can like have an overview. So when we have something like this, I don't know if you can like, can we have like a screenshot? Take this. This would be this over here. Yeah, works. Okay. So um, so okay, so there's like an opening bracket and like there'll be a bunch of stuff like this, and there's a closing bracket at the end. So this is like okay, this is like semicolon, I guess. Um, so we have like this keyword and enum keyword, then there's like the type of the enum, then there's like braces, at the beginning and the end. Inside the braces we have like a bunch of stuff separated by commas, and in each of those we have like a certain kind of enum, and then we have this part equals some literal, um, and as you can see, like there are some like so there are like rules to it, like we don't need to actually specify this part everywhere, so we can just leave it. And the language is supposed to interpret that this should be 101 and it should be 102, and basically it just increases by 1 unless you just specify something to be equal to something specific. It just follows this logic. And if you don't specify anything at the beginning, like in this language, it will consider it. I mean, this is C++. It's not my language. So in C++ also, it's like the first thing will be taken as 0. So what we are doing right now is like we are just reading this as a human because we understand this language, but we need to do that for the computer. So if we are making our own language, we need to do that. So how does this happen? We need to go down to the most fundamental level. So right now what we are doing is we are trying to parse this text. So we are trying to like take this is a keyword, this is some name, or we can call it an identifier. This is some kind of this is a left bracket, this is a right bracket, this is like a semicolon, or you can call it in a formal sense a delimiter. This is a separator or comma. Then these are also kind of identifiers, all of these. This is an operator, a binary operator. This is a literal. And these are also like, okay, this also I just left this out, but these are comments. And comments are not going to be part of the code. It's just that we want to know that we have to ignore them. So there's all of that. But as you can see, like what we're doing right now is we are taking these chunks of characters. So we have this thing enum, which is one word, but I mean it's not so simple. So you might think that okay, it's like separated from this thing by a space, so that's how we know that this is a keyword, which is okay. But if you think about it, you can have something like if this was written as token. Okay, let's just write tok equals 0, and there are no spaces here between anything, but we know that this is still separate, like this is a word, this is an operator, and this is a number. So there are parts to this thing that do not necessarily require there to be spaces between the thing. So that makes the thing a little bit more complicated, because now you realize that you can't just assume that things will be separated by spaces in order for them to be different tokens, which is the more formal way to put this. So these are all tokens that we are talking about. So that means that we need to have some way to be able to obtain these tokens, and that needs to be done before we do anything else, basically. So even before we can begin defining the grammar or the rules of the language and what things are supposed to mean and what the computer is supposed to do, we just need to be able to work on this task of being able to take these things and just be able to solve this problem of like, okay, this thing ends here, and this is a different thing, and this is a different thing, and like, and so on. Um, and they're like it's actually not that complicated, it's kind of very simple. I mean, and this whole process is kind of, I think you can call it tokenization, or maybe a more formal way of putting it is like lexical analysis. And this stage is it's a whole stage, like you um, the uh, I don't know, like how to put it, but so you create an object called as a Lexer that kind of keeps track of these tokens. An object, or I think people associate object with classes, but it's like a struct basically. So I can show that here. So I have this Lexer.h. So This is the, I think, probably the first file that I created in this program, in this project. Um, so this struct, it's become very big now. This struct, which is a Lexer, it records this basic thing. Um, it's gotten complicated by a lot of other stuff, but really the main part of this is like the tokens and this part here, I guess you can say, or even this. So this is kind of the main part. Uh, and okay, so we are keeping track of some information like uh, this is like related to the file. So what, because actually when you compile, like when you can have a project where you're compiling multiple files, so you need to have the lexical analysis being done on each of those files, and also it's more than just that, because so in the language even that I have created, I have something like hashtag include, which means that you need to, like in C and C++, you just take the code in some other file that you're including, and you just copy that into this file, and so you need to be able to tokenize all of that. So basically, you're going to be dealing with multiple files. So anyways, and yeah, you need to keep track of the file name, because so there's one thing in the compilation process that people also need to know, that which is very like fundamental, but it's kind of important, is that a compiler, one job of the compiler is to create that executable which will run on the computer, but another job is to also tell the user where they went wrong if that process fails, which everyone knows, because like you write code that is wrong and then you get errors in that process of building it, which is not a non-trivial thing exactly, because I mean you can't just assume that you will get errors, like because when something fails, like it's also possible that it just crashes and nothing happens. But if that happened, then it would be much more horrible for a user who's like, using the language, because you would just write some program and the thing didn't compile, and you would have no idea why it didn't compile. So what we want is, in any decent compiler, to have some kind of a interface that tells them what went wrong in the code that they wrote. So for that, what you need is, like, you need to know what file the error came from, and what line and what position in that line where there was something written that was wrong or unexpected by the compiler, and so that way, like, you get good error messages. Basically, like, you can identify like this line and you can display that line, and you can like show at this point in this line was like wrong or unexpected, and like this is what it should be, and so that's how you can like print messages in the errors. So you need to keep track of that information. So with every token, you kind of like store information of that kind. So we have tokens, and token itself is a struct. It's, I think, coming from tokens.h. Then we have all these like commands, functions basically, get next token, peek next token, and all of this stuff. So in our process of doing this whole thing, we are going to go over the file, which is, you can now think of it as just a bunch of characters, because fundamentally that is what it is. Just like this file itself, like it's struct space lexer space bracket opens new line, then there's like a tab or something, then st. So like this whole thing is like really a stream of characters, and what we want is to go from that character stream and um, get like so we have like a character stream, and we want to go from this to a bunch of tokens, and the thing that does this is the Lexer. So this is the first part of the whole project that you need to work on. So I think the way to think about the compilation process is kind of like it's a bunch of mini projects in a way. Like making a Lexer, or yeah, Lexer is like kind of, I mean, it's a tokenizer basically. So like a tokenizer itself is kind of a project. Like it's a very minimal, very small project, but it is a kind of a project, and there is a way to do it well. like there's a way to do it badly, which currently like the way I'm doing it is actually a very bad way of doing it. Like the way right now I'm, I think, doing my tokenization is like I just read the line from that file and then I tokenize that, and I mean I keep track of stuff like if it's like a multi-line comment and everything to handle that, but I'm still kind of like going line by line and tokenizing it and in a loop. And like that's like very bad actually. I think I don't know why I'm doing it line by line. Like for some reason, I think I thought maybe reading the whole file in one go into memory is bad, but maybe this is even worse. I guess I don't know. But basically, that's not the right approach. I think reading the whole file into memory for very large files is also going to be kind of slow. So like the most optimal approach I think is just something like memory mapping. So you kind of map stuff into like virtual memory, and then you take a pointer and just go character by character like, through that. Um, uh, so, so basically, my point is that like you can take something like this and you can even think about it very deeply in terms of like not just building it, but even to improve how you go about it. Even I have to like kind of do that. I haven't done it yet. It's like it's an issue actually. I've put for myself like I kind of keep track of things to do, like rewrite the Lexer for performance. I've kind of kept this over here. Um, but yeah, so this is kind of the first part of this whole thing. So we kind of do that. Uh, Tokens, I think, can let's see what is happening in this. So here, I think I already, like I think, yeah. So this is a token type. If you go at the bottom first, um, yeah. So this is token struct. Yeah, a token. So val is just the token, like the word itself. Like what is the token basically? Then every token has a kind of a type. This line number position, like this is for the error messages. So if you have a token and while you're compiling your program later on something goes wrong, I can just go into this token and like read this information so that I can print my error messages. So I'm kind of doing that. Token type. So this is important because later on when we are going to parse these tokens, which is going to be the next stage, we kind of need to know like there's some like all tokens are not the same. Um like this enum, like the reason why it's in white color is because this is a keyword. So this is a token keyword. Like in my language, I would have like a type called a keyword, token keyword. Then this kind of stuff, like just like stuff that's basically just names that you have defined. These are identifiers, like it's stuff that you have defined. Then there's a left brace, right brace. Um, like these numbers are literals. So literals will be like kind of stuff that you assign to variables. You can think of it, I think that. So that's like integers, floating point values, decimal value basically, and string values, some kind of text string in brackets, just characters, like single characters. So all of these are like literals. Uh, so a token, I mean literals can be itself a type, but I found it more useful to like break it into specific types because literals like a numeric and a string literal is different, and even boolean actually true and false. So you want to treat them in different ways. So it's useful to just specify them whenever you can. I think data types also. So that's a kind of a token. Int, char, float. These are data types. Equals is a kind of a type in itself. So I think most of these tokens would be like operators. So all of these are operators. Many operators are there, so you need to have like tokens for that. And in operators, you can see like there are like some that they are like more than one character. That is this whole thing. So for example, like plus equals is kind of made of plus and equals, but it's not just plus and equals. So if we didn't have this token, then it would have been treated as like a plus and an equal, as basically two tokens. But this whole thing is supposed to mean something else, because a plus equals 2 is mean equivalent to like first adding 2 to a and then assigning that value back to a, which has a whole different meaning. And so it is just more useful to like have tokens specifically for this purpose. Anyways, yeah. So, and I had tokens like specifically for like other purposes, like so I have these two tokens which are um, so they are like context dependent. Basically, I have even mentioned it here. So um, I mean, I've written non-context free. It's kind of I think the same thing basically. Um, thing is that a star symbol can mean two things. It can be multiplication or it could be like the pointer dereference operation. Uh, and you don't know that at this stage when you're just making the token from the character string. That will be something that will depend on the syntax when you're going to do that parsing, and you will see that this thing comes before this thing and this thing is after this thing, and you kind of begin to see the structure of what is being written. So you kind of need to know what is going on around this token to be able to actually interpret the meaning of the token itself. So it's kind of an ambiguous thing. So I mean, there is a token for it, but I haven't called it token multiply or token pointer deref or something, because I don't know what it is. So I just named it a generic kind of thing. And same goes for ampersand. Like it can be a binary bit and operation or add or sub. So I think just these two tokens were of that kind, but everything else is kind of clear, I guess. Um, yeah, the rest of this is just specific to my project. Um, so that's like the broad overview of the lexical analysis stage. It's kind of a boring stage to program, because it's like you're just reading characters in a loop, and like you have to go for every kind of thing. You have to like go character by character, and it's like very tedious and irritating, and everything feels very repetitive, because for everything you kind of need to do the same thing. It's just like there are different conditions in different places and all, but it's sort of like just reading characters, and like whenever you find something finally you just make it into a token and like store it away, and then you continue, and basically that is what happens. But it's also kind of like important, like you can't get this wrong. It's like fundamentally like the most basic thing to do, so you can't mess this up. It's important to not mess this up. So this is that stage. Okay, I think we can clear this. So we can move on to like parsing. Um, okay, even before we go there, I guess I should just show. So Lexer.cpp is where I have the actual code for my Lexer. So performing lexical analysis is this function where it's happening. Um, and so here you can see like I'm doing this get line thing, which I want to change eventually. I don't want to like read line by line, but it goes line by line right now, and then I'm running this generate tokens function, and it like uh, basically I think it so the Lexer object is kind of uh, contains everything that I need, so I don't need to like move things around in the function as arguments, because this thing is contained in Lexer itself. Lexer line contains that line in the file, and like I just need to pass Lexer everywhere. So this Lexer, it's a pointer. I'm just passing it everywhere where I need it, and in the end I just return the Lexer as well. The Lexer is kind of the fundamental thing that I'm using. I think it's used even in the parsing stage basically. Okay, so and yeah, this generate tokens is like this huge. So as you can see, it's like the whole thing is very repetitive. It's very ugly, but kind of works. Um, yeah, generate tokens. Yeah, this is the whole function. This is the whole loop. So yeah, that is this thing. Um, so Then comes the parsing stage. So okay, um, how to so okay, I'll just go over here. When we have anything in a program, so we have like so we have some if statement. If A greater than B, then you have a bracket. Then you print something, print F, um, something, whatever. There's some semicolon and whatever. There's like closing bracket. Um, so basically, like you have something like this, right? Um, so uh, now in the Lexer stage, you will kind of break this into tokens. So if is a token, the bracket is a token, A is a token, this is a token, B. Right? So now you have obtained something that is finally workable in more human readable, in a more human readable sense, and you can like now work at actually interpreting things. So uh, but before we interpret things, we need to kind of perform a structural check to this whole thing. So it's sort of so parsing is basically kind of it's actually two tasks. It's one task is syntax analysis, or I mean we can call the whole thing syntax analysis, but it's syntax analysis in like checking the syntax. So it's like checking if there are mistakes, and at the same time there's another part to this which is actually a crucial aspect, like probably the most uh, like the basic point of the whole process, which is to create a thing called an AST, which is an abstract syntax tree. Again, I think one might argue that this is not fundamental to the process of compilation itself, and we can maybe do things without this, but it's so basic and intuitive, and it makes sense that I think almost every compiler uses this process. So you make an AST basically always in any compilation process. Um, so before we go there, so let's like see like so what's the point of this? So the problem is that maybe you could just have someone who wrote something like greater than AB, if greater than AB. So is this correct or not? So the thing is that in your language you would have to define the way you do things, and in something like C and C++, and even in my language is basically just equivalent to that right now, equivalent to C or subset of that. This would be incorrect because your operator comes in between A and B. This is a binary operator, and you first have like one thing, then you have the operator, then you have B. But in something like Lisp, like there are like many Lisp languages, like you could have something like this, and this would actually be the correct syntax. Like you would have something like plus 2 5, and this thing would be interpreted as okay, this is the operation, and now it waits for your operands, and you pass the operands after that operation, and then it will understand that okay, this will act on these two things. So that is also a valid syntax in that language, but this is not the valid syntax in something like C and C++. This would be the valid syntax in that. So this is like the part where we get into the specifics of the grammar of your language. But most languages would usually have something like this. Usually, it's like more intuitive, I guess, because people just read this normally in many places. This is kind of a weird way to read things, but I guess it doesn't matter to the computer really. It, I mean, one might argue maybe even this is easier to parse. You kind of use a stack and you just push things and like all of that, but it's kind of it's just bad to read. So I think this is like how we usually do things in most languages. So, but the point is to say that we need to kind of go over our tokens, and we need to figure out whether the structure in which those tokens are arranged is actually correct. So that is kind of the way we do it. So like even this statement. So this is an expression first of all. This is one expression. Uh, and expression itself is a kind of concept because you can have so you can have like something that's like go to some code I think. So yeah, this is I think, a recent example. So let's take this. this. Let me clear the yeah. So maybe even a red pen as well. So here we have a function. If we ignore the inline for now, we have a data type. So what are so okay, before even we go there, so this whole thing, this is like the function definition basically. Then we have a bracket, and inside this is going to be a bunch of stuff, and then the bracket closes. So this is the topmost level of looking at this structure. What do we say this is? Like this is a huge thing. So this so these curly brackets in these kinds of languages. So this kind of creates a scope, or I'll call it like a block. So we have this whole block, and in a block you can have many expressions. Like there's one if statement, like an if expression. There's another if expression. Then there's a for expression. Then there's another for expression, and then there's like just a normal kind of some other expression. All these are expressions. So you have it's basically kind of, it's a list of expressions. So it's a list of expressions, and each of these expressions itself has to have some other definition. Like this is an if expression. It also has a structure. So as you see, like there's like curly brackets even to this. So there's an if, then there's a condition. So there's like this if keyword, this is a keyword. Then there's like parenthesis. Then there's some condition inside. Then there's this whole thing, which is another block. And then the rule for blocks is that inside blocks you have a list of expressions, which is the same rule as outside here. And already you can, I think, get the idea that what we are doing is kind of, in some sense, recursive, because what we have is something like this is a list of expressions, and inside we can have an expression, and that expression could itself be of many kinds, and there can be some kinds of expressions which have a bunch of expressions inside them. Basically, this is a block. So you have expressions inside expressions, and there are different kinds of those expressions. And so this is like, as soon as you think of this, like you should think of maybe like a tree. So at the top level, like you have like this function definition, like you have a function definition here, and inside this, like, so there's like a block, and the block has a bunch of expressions inside it. So there's like an if expression, then there's another if expression, then there's a for expression, there's another for expression, and then there's just something else. Then this if expression itself has some statements. So then there's like some expression here. There's then a return here, a return expression. Again, similar for this. This itself now has an if inside it, and actually this only has one thing in the block, so that's fine. It could have had more things, then we would have had more stuff here, but there's an if expression, and this if expression itself then has like something, and then a return. So you can already see, like, so basically this whole process is like you're kind of constructing a tree, and this tree is kind of the most critical part of this whole process that we are doing up till now, because it kind of defines the whole grammar of your language. Like, it's the way you do it is going to be as per like what the rules of your language are. So like, because and while you're doing it, you obviously check the syntax. Like, if we are doing this, so we are forming this tree, we have started and we created like this part of the tree, then we went to this part, and but here maybe instead of this it would have been written equals current and something like that. So this is wrong. So then as soon as you come here, you stop and then you need to like go and print some error message. I don't know why I'm writing it out. Basically, like, so you go and like you print an error over here on the console, and uh, and then you actually have to continue. Actually, I was working on this right now. I have not completely worked on it. Like it was kind of annoying, and I just stopped in between. Uh, but yeah, the point is like you continue after finding an error, and you continue making the tree and everything, and obviously if you find an error and you can make the tree, the point of continuing making the tree is not that you're going to maybe use the tree, but it's more like uh, just to continue this whole process so that you can possibly find even other errors that might be there in other parts of the program, because if you just stop at one error, then you might not be able to know about other errors that are there, and the person who is going to actually write the program will have to like keep fixing one error at a time and then compile again and see the other errors because you are not showing them. So that would be very bad, uh, just for usability purposes. So what you want is to kind of skip over that error and then continue. But broadly, this is what's happening. So you're kind of constructing this tree, and this is like one function. So you can have other functions, and then you will have actually this thing which will be one branch of another bunch of things, and this whole thing that you're going to construct is what we call the AST, which is actually the full form of that is abstract syntax tree. So that's the thing that you're really constructing in the whole parsing stage. So to go to the program and you can see where that's happening. So AST.h is the place where I've defined like all these different kinds of expressions that are part of like this tree. So like function definition is one kind of an expression. If expressions, for expressions, return expressions. So we need to have types. So there is an expression type enum. Like you can have. So actually, at the most fundamental level, if you have an expression just like a is equal to 2, semicolon. This is an expression, and so this whole thing is an expression, but there are parts to this as well. So the parts of this expression are this, which is an identifier, then this, which is a literal, and there's a binary operation that's happening. So whatever this expression is, there's some expression, and there is a binary operation that's happening on this, and the operation is happening on some identifier and some literal. I think I've kind of crowded this whole page, and I would have, I think, defined it as a numeric literal, or maybe uh, maybe in depending on how you write the compiler, it could be specific, even more specific. It could be like an integer literal. Uh, but yeah, in my language, I've just kept it like a numeric literal. But yeah, this is kind of the part of the syntax tree for this particular expression. So this would be like the thing happening here. So basically the um, the goal of this whole stage is to now use what tokens you have and form this kind of structure for everything. So if we like declare everything, so at this stage, what we are basically doing is we have our list of tokens, um, and we want to construct an AST from that, and this is the goal of the parser. So basically that is what is happening broadly at this whole stage. The first stage was just creating this from like raw characters. So we had just this is like a W that's elongated. Damn it. Okay. So the Lexer got us to this point, and then the parser takes us to the AST. So this is like the next part. So this is like the next mini project in this whole process. Uh, the parser is supposed to do all of that, and so just before I go there, these are all the AST expressions. Like we have, so since this is like kind of, so a bunch of these things are repetitive. So I've basically used inheritance to define these expressions. There are many kinds of expressions. As I said, like they identify as a literal function definition, if, switch case, for, while, declarations, unary binary operations, and so all of these things basically. And for every kind of expression, we have a struct associated. Like AST expression is just the base expression type. It's like a struct, and everything inherits from it. So identifiers, littles, function definitions, if, case, switch, and so basically the whole thing. Um, and like for some of them, like you have something specific, because so whatever stuff is going on here is like something like if you have an what is an AST declaration supposed to be like? What is this expression supposed to be? So like if you have a statement int x equals 5, the idea of this is like you have a data type, then you have an identifier, then there's like this operator, then there's this literal. So basically you need to like break this whole thing, um, and form this what do we say, you have to form this, like you have to convert this thing into this thing, and the way you do it is that this thing would be defined as uh, like this data type. You need to store the data type. Actually, I don't know what I'm doing. It should not, this is not exactly this. So it's not an expression actually, it's, this is just the information that is stored here. So okay, so data type is like part of the information. Okay, I think I was not wrong. I shouldn't have roughly. Yeah, so data type is the first part. Then you have a binary operation, which is here in this case it's the equals operation. Then this acts on the identifier x, and at this part there's another. So this thing could have been anything. It could have been like this crazy like expression. Like you could have anything, right? Like this thing could be a whole expression. So basically, this is supposed to be any kind of expression. An expression that's actually supposed. It's specifically an R value expression. Okay, I don't know. So um, so it's not a like a crazy idea. R value is like fundamentally basically just anything that is possibly going to be at the right side of the equal to sign. To be more specific, basically, the thing is that we want this thing, whatever is there at this side, to be able to return some kind of a value to us so that we can go and assign it to this variable. Because you can't have something equal to like x equal to like int in this language at least, because this is not an R value, so this doesn't return anything to x, so this is just invalid. But something like maybe if you had some y plus z and y plus z were some variables that were defined somewhere, this is an R value expression because like you can evaluate this and whatever value comes out of this can be assigned to this x here. So that's like, so this is particularly not just any expression, it's supposed to be an R value expression, and in our case this is just like literal, it's like just 5 in our case. So yeah, that's basically like broadly what happens. This is like an example of what is happening here. So like here we are storing the data type, the name of the variable. So I didn't mention it here, but okay, I mean like this is like the name of the variable. And Oh, okay. I think I'm. This is not actually the whole thing. This whole thing is like one expression. I shouldn't call this declaration. Um, so a declaration, yeah, because declaration actually is something very specific. So declaration could be just this. I forgot my own language. Uh, a declaration could be even something like this. You don't actually need to have an assignment after that. That's like optional. So this is specifically just the declaration part. But in something like this, int x equals some expression, this whole thing is just an expression, and this is the declaration, AST declaration, and this part is another expression, and this is the operation. So actually, the way I probably should have written it would have been like um, so this thing would have been like some expression, and we would have like some AST declaration here, and then, and even maybe actually to be specific, this is like it's part of the binary operation. And then you have some other expression, some R value expression. Yeah, so this whole thing actually this whole expression, and this AST declaration has your data type and this identifier. Yeah. Anyways, I mean this is just structural stuff. Um, I'm forgetting like details because I'm like talking while like describing the thing. So, but basically like it's very kind of basic. Like there's nothing deep about it. Like like a binary expression has like a left expression, a right expression, which is obvious. Um, Declarations are like this. While statement has like some condition, and then it is a block after the while loop. So you have a block of things. It's a list of expressions. So all of this is sort of intuitive. For expression has some initial stuff, some conditions, some increment, and then there's a block. So basically, this is the way the whole thing goes. Um, I don't know if this is necessarily the most optimal way of doing this. Um, I mean, I'm just doing this for the first time, literally, without like kind of any resource or anything as such. It's kind of it kind of just makes sense. I mean, if like thinking about like how ASTs are and like if you need to like parse something and construct it, so it just seemed to make sense this way. So fine. So I think that kind of covers pretty much most of this. So I can go over the parser. See, this is just ast.h. So the actual code is in parser.cpp. This is a little more convoluted. So we parse the tokens, we get this. So we have the Lexer object itself, which we pass in, which contains all the tokens. We define our AST. Then we just go over the project, and then everything is like specific to the language also. So it's partly language dependent, but basically that is what is going on. So this stuff that's like global at the top level. So in my language, like so you can have stuff that's sort of like you can have enums and structs, um, and maybe you can have like declarations and stuff like that, variable declarations that occur outside any function. So at a topmost level, like we have functions, right? Um, in any language, like these are all functions, right? So this function, the function here. So the question can be like, in your language, do you want to allow things to exist outside the function? So there's no function, but you just write an expression anyways. So is that expression allowed to exist in this global scope? So all of these things, these kind of things, at least for now, I've defined these many things. So I think I started with type defs. Even that can be done. So all these things can be done at the global scope. Within functions, then of course you can have like if statements, false, like many other things. But like you can't have an if expression at the global scope in this language. But like for example in Python, like you can do that. Like there's no barrier to that. So yeah, I mean like there's nothing special then in all of these. So all of these things are just going over the tokens, and so it kind of takes tokens uh, piece by piece, and so all those functions that showed earlier, I think in the Lexer, um, like these get next token, peak next token. I don't know if I mentioned these, but these are supposed to be used in the parser at that stage. So when we are going to go over the tokens and even this current token index, so actually I mentioned it for parsing. Um, so I'm keeping, because I'm storing all the tokens here, but I need to like go over the tokens, and and there's a difference like peak and get is, for example, um, peak would be like your add this token, but I want to see the next token, but I'm not going to move there. But if I want to like go over the next token, like I'm just moving ahead, then you just do get next token, which also changes this index. So there's all of that stuff. I mean, there's like kind of there's nothing like deep in this. It's just implementational stuff. Um, okay, so till here it kind of covers most of what is called like the front end. Like there's one more step um, beyond this. So after doing all this, we kind of have like a syntax tree with us, and so we need to like remember like what was the goal of the compilation process. So the goal is to like have like a set of, I mean, goal is kind of like in a very basic sense, you want an executable that we can run on the computer. But at a very low level, we can think of it like it's also like you can think of it as in generating assembly instructions, right? So instead of language constructs like for loops, while loops, if statements, we want something like a kind of an assembly which will have like raw instructions that actually the processor understands, uh, jump expressions, move, and all of that. So all of the stuff we have been doing till now is to be able to just kind of convert our text file into a format that can be easily processed in order to generate those actual instructions at the end of the day. Because if we started with just raw characters, we don't know like which token is actually a token and what's not, which we mentioned in the beginning. Then if we have a bunch of tokens, we don't know what is the right way to write them. Like we have to have certain rules in our language, like greater than a b doesn't make sense, but a greater than b makes sense. So we went through that. Then we had to have a structure to the whole thing. So we have that now. So the AST kind of defines all of that for us. So then we kind of reach the final step, which is uh, I mean it's not necessarily the final step, but in my case I'm kind of doing it uh, in the simplest way. So um, basically we want to generate that assembly, but doing it directly is also not so simple, or rather you can do it, but it would not be the best idea. The problem is that assembly language is targeted for a particular processor, so you can have like an x64 processor. There are like ARM processors, and there are many other processors, right? So we have different processors. Every processor has some assembly language. They have their own instructions and stuff. Like there's even the x86 processor, so even before x64, which is just 32-bit. This is 32-bit. This is 64-bit. So all of these have their own like ISA, their own instruction set, um, and so you right now we went through like we got tokens, we got an AST from this. So we could just go and like kind of go through the AST and emit instructions for everything like directly. But then the problem is that this will only run on like x64 machines. Like the whole compiler will basically be functional only for a particular processor. But usually you don't want that. What you usually would prefer is that if I'm compiling my program on like an ARM machine, then it will compile it for that target. And then so it should basically be able to maybe, or not necessarily on the machine, it's like maybe I can specify like a compiler flag and tell it I want to compile this for this particular CPU. Um, but if your language, if your compiler logic itself is like very hard coded to be able to emit those instructions for that particular processor, then that would obviously not be able to handle the other targets. So the way to handle this is to not do this, but have another step in between, which is to emit something like an assembly, but actually it's not a real assembly. It's an IR basically. So it's an intermediate representation, which is almost like assembly in the sense that it is kind of just a bunch of instructions fundamentally, and this thing is sort of because you have defined your own like IR, then uh, maybe you can have a way to translate the IR into each of these. And again, doing that, if you have to do this yourself, that's also still like difficult because you have to like do the translation for every single processor and handle every single thing. But here is where there's like the advantage that this step is already done by people who have like created this particular app. So, for example, what I'm using is LLVM. Um, so LLVM itself is like a particular IR language in a, like that's one way to put it. Um, but the advantage that you actually get is that LLVM in itself, it has libraries that handle this whole part of this process. So this particular part of the process, which is we call this like the backend, you can say, like this is the backend of the compiler, the backend of the compilation process. You go from the AST to this IR. So everything like from here, it was like raw characters, um, tokens, AST to IR. This whole thing is the front end. So this is the front end of the compiler, and then like this thing is like the back end, and this is like one way to like divide it in a intuitive way. But the reason like why we are dividing it is also like specifically because in this case like the backend is something that you can use from someone who has already provided that to you, and you don't have to write it on your own. And the advantage is obviously because there are like probably like dozens of these targets and they have their own instruction sets, and writing that is like like insanely like tedious, and it would like take years of effort, and it's already something that like LLVM provides, and like there are other also like the LLVM is not the only one, it's like one of the biggest ones. I think there's something like MLIR, I think, I don't know exactly. Like there are many other, not many other, I think I've heard of these two. Um, but yeah, I'm using LLVM for this one. Um, I think both of LLVM and MLIR I think were created by Chris Ladner. I think Chris Ladner also created Swift. I'm not wrong. I don't know. It's the Swift language. He worked at Apple. Um, so yeah. So I mean, this is basically the thing that this gives you. Like it provides you with this. So it's a kind of a whole language in itself. It's kind of an assembly. Um, but it has, so the way you use it is that there, like LLVM has its libraries. So um, like if I go to llvm.h, here there are all of these libraries I'm including. So all of these are LLVM libraries, and I've even divided them as per like what purpose they are solving. So for the backend stuff, so when I go from my IR to actual like target code generation, I need all of this stuff. Then there's some other stuff like I need for some other things later on. Um, and these are like some basic libraries which I need. Uh, we go, so the backend is in like main.cpp. Yeah, here I'm like running the backend. So I mean this is all, and this I don't even know like the details of this. So I think I probably just took help with ChatGPT to write this, because like LLVM is like something that, so whenever I have to like work with a library which is like a huge library with like bunch of like different methods and stuff, like I don't like to like learn like 50 methods to be able to do something, and then I'll have to like read the documentation. I mean I could do that, I mean that is like probably the traditional way of doing that, but it's like just uh, I don't find it very useful if it's like just a side project, especially like what I usually do like, in my free time. So I just like use like ChatGPT for these kinds of things. Um, but yeah, I don't like generate code like in the agentic sense usually for side projects, like because I try to like do things as controlled and manual as possible. I just want to know what I'm actually doing. So I probably like generate snippets, and then I just kind of copy paste them, and something doesn't work, I move it out and I maybe modify it. Yeah, so this is that part, and so that's the backend. Um, this part kind of is handled by LLVM mostly. Just is this like small amount of code that takes care of that. But you still need to get to this IR, and going from this to this is basically the final major step, um, which is the IR generation. At least I have called it that. And so basically in IR generation, you what you basically do is you just go through your AST, and for every single kind of AST expression, you define a code generation function, or like uh, like I call it IR generation, I think, which the goal is that you use whatever information is collected at that level in the tree, and for that expression, and you translate it into some kind of some LLVM instruction that emit like some IR for that particular thing. And the LLVM is like, again, it's like it has its libraries, and you have to like follow some things for that. So I mean, this part is something that, because it's involving LLVM, so it's a little bit opaque to me. So I have kind of um, I've like had a little mix of manual work and using ChatGPT to help me in a lot of places. Um, like as you can see, like so all these AST expressions, like they have like this generate IR, not this one. This, well, that's also, but the main one is generate IR. So all these generate IR functions are being called for every kind of expression. So AST function definition is generate IR, and this generate IR actually comes from, if you go to AST, you can see like I have this generate IR and it's being overridden because it's defined in the base class. It's just virtual method, and it's overwritten here and it's defined actually in this IR generator file. And I've defined it for every one of these kinds of AST expressions. So, and the thing is actually happening from here. So I have this emit LLVM IR, which I call. So we have context and modules, and these are like the fundamental things that LLVM has. Like there's a context, LLVM module. So every file is basically, I think you can think of it as a module. So I have that file that I tokenized, and then I use the parser to create an AST, and then I'll emit the LLVM IR for that file, which will be like a module. I think that's one way to think of it. And LLVM also has this thing called the context. I think it keeps track of, like, I don't know, maybe addresses or different kinds of variables or functions or something. Like there's all kinds of stuff. Um, the builder is like the thing that you need to actually create and emit like blocks and stuff. Um, yeah, anyways. Um, so this is like for creating one module, you do all of this and this happens in this loop. Like then it traverses over the AST and does all of that. Um, but like in the case that you have multiple files, like you will have this thing going on for multiple different modules, and then comes the challenge that is actually the next challenge after all this, which is um, the linking stage. And this is like one of the irritating parts of all of this, because again it's like partly because it involves LLVM, and I find it opaque just personally, not LLMV. So LLVM. So LLVM modules, we have a module. So we can have one module and another module, and we can have many modules for different files. Now the thing is that each of them also has some kind of a context. When we are creating these, as you saw that when we are emitting it, we defined some context. So all these have some LLVM context associated with them. But the problem is that because all these are part of the same actual program, it's just that you have defined stuff in different files, but it's supposed to be one single executable at the end of the day. So you'll have like a bunch of instructions that are like, it's just one whole thing. It's just like it's organized in different files, like for us to use as humans to program. But it's not actually supposed to be that for the computer. So the problem is that like you need to bring all of this under one context. So I think one way to think of it is, I'm not, this is kind of where I might go wrong in things, but this is like probably like how I think of it is that maybe if you define something like x equals 1 in one file, and in another file you had also some x, or maybe like int x equals 1. Here you had some float x equals 1, and both of these maybe are like global things and something like that. I don't know. Those 5 points, I don't know. So you have some variable called x. It's also an x, and it could be that x is internally somewhere it's stored at some memory location, and this x is also stored somewhere. So so we need to know that like this thing is true for this file, this thing is true for this file, and when they were parts of their own files, then they made sense. But once you need to bring those files together, you kind of need to resolve this thing. So you need to know that these things are not the same. So it's like this should be like some x1 and this should be some x2, and this thing when it's defined, it's supposed to be defined at some memory location, and this thing then has to be at some other memory location. So if by chance like if they are defined at the same memory location, and you just bring them together, and they have like different meanings, and this is an int, this is a float, and so then it will be obviously a problem. Um, so this thing needs to be resolved when we like bring different modules together into one single shared module. So to do that, you kind of need to. So the goal is to obviously link the modules, all of these modules, whatever we have. So we need to link them into one single module. But you can't just do that directly because these modules are all parts of different contexts. So all of this also, it was kind of not something that I immediately understood. It took me a lot of time to do it with many things that went wrong. Probably I still don't fully understand it, but this is like part of what I now know after going through this and fixing these issues. And I think now it's pretty much workable what I made. So you need to bring all these into the same context. So the way I am doing it is I create a shared context. So I create my own new shared context, and I move every module into that shared context first. So every module is moved into the shared context, and once you have every module in the shared context, so in the process of doing that, it probably LLVM probably internally just resolves these kinds of issues, I think. Because when they are in different contexts, like they don't care about each other because they don't know anything about each other. I think that is one way to think about it. But if you move modules one at a time into some shared context, now this is the same common context, and um, then it kind of looks into stuff like maybe if you define something like some x somewhere, and it's defined at some memory location, then obviously this other x, I mean this x is defined here, then this other x is supposed to be given some other memory location or whatever. I mean this is probably not the best analogy, uh, but yeah, my point is basically that when you move things into the shared context, then it will be able to know that it needs to handle things that are going to be different. So after moving those modules into shared context, then you just finally are able to actually then use the linker. So the linker is in part of LLVM itself also. This is like the LLVM linker. Um, because then you just take the modules and link them. Um, so you take all modules from here, um, and you just link those. And this is all like very messy. Um, so all this is happening in main.cpp broadly. Um, hmm. So yeah, here so I have this loop where I'm compiling all of these things. The compiling basically means for one file, I'm compiling that particular file, and it does the whole Lexer, parser, and IR generation stage, which is the front end. So this is basically just the front end for one file, and it's happening in like multiple threads. Um, and then I'm going into the shared context. I've created a shared context, and I move every module into that shared context, and after all of that is done, then I finally link them. Okay, there's like some other stuff which is related to linking other libraries and all, which is separate, but basically I link the modules. The link modules also is like this function. Um, I think it's happening here. Yeah, link module. So it's basically just LLVM related stuff. Yeah, basically this is like the thing that's been called linker.linkin module. And you just move the list of modules, not the list actually, it's like one at a time. You move this in a loop, and yeah, then you just return the link module. So yeah, that's like basically like the final thing that you need to do, just to be able to handle multiple files using LLVM. And yeah, basically I think that kind of covers everything. Like once you're done with that, you so you've gone through the Lexer. Um, Gone to the Lexer, then the parser, then the IR generation, then and you do this like this is like for every single file. So this is like one file. Like there'll be other files like this, um, and you do that, and at the end of this you get some module. Um, Same goes for all of these, and all of this is happening in all of this is in like parallel, in like threads. It's and obviously you need to handle like using mutex logs things. Um, Threads obviously means that like it's not like for 100 files there are going to be 100 threads, like because your CPU can only have like a certain maximum number of threads that are actually parallel. But yeah, basically that is like what you're doing. Then you have like, so you create all these modules, and then once that is done, you have to move them into like some shared context, and all this is like then all of this is like these are LLVM related modules. So this is all of this is like from here on. This stuff is like largely supported by LLVM. It's not like I'm doing things manually, like completely from scratch. So LLVM moves it into some shared context, and you get them like a unified module. I don't know, like some unified module from this. Or you can say like linked module. So this thing is like the linking stage, really. Because if you just went from here directly, you could also go and like what is this? Um, it is possible to like just go from here and directly create, like for some target you can create you can run the backend directly. If you run the backend and you got a dot o some object file, and you could do that for every one of these files. You could just create a dot o separately. But what would this be? Would be like uh, it would have unresolved symbols in it. Like you defined some kind of like you could like use some function definition, like a function prototype, and you're using that function in your program, but the function is not actually defined in that file. That function is defined in a different file. So you're having a symbol, which is that function name maybe, and it is part of your this object file. Now it's like used in different places, but whenever there is going to be a call instruction that is made to that function, it will not be able to go and jump to that function because it doesn't know where that function actually exists, because you have not linked it with anything else. So it will like be like just an unresolved symbol. So you can't actually then create an executable from here, because it will like at the final linking stage, when you go on and link other stuff to create the executable, it will like fail and say there's like unresolved symbols. So you could do that, but then actually what we are doing is like we are creating one single module. So we have solved that within this process already, and so that is done. And you have like this unified module. Now as for libraries, like if you have like hashtag includes and you're like including some libraries and something, and you need to link those, so you could have like at least the way I'm doing it right now is like I have like LLVM bytecode libraries, um, LLVM bitcode. So these are like programs that I have like an, uh, like just manually compiled using LLVM into bitcode files. Um, not necessarily using LLVM. How would I say? So like it could be like even just like I have written like let's say C++, some C++ library, let's say for printing or something else. So we have written some library, and it's written in C++. And remember that this whole thing is, this compiler is not a C++ compiler. It's a compiler for my own language. So this whole thing, I would like write the programs that these files are. These are not .cpp files. Like in my case, these are .m files. Like in my language, I've just called it that. Uh, but because like you have converted this into like some kind of a object file now, so it's language agnostic at this point. So you can actually have libraries that are written in a different language, then you can convert them into some binary and you can link them. Of course, like this is where there are going to be issues that could occur of like ABI compatibility, uh, which need to be resolved. Um, but that is also like another issue that it I know this also partly because I was trying to implement periodic arguments, and I kind of mostly was successful in doing it, and it kind of works in some cases somehow, but it fails like when I try to use printf in my language for some places. But um yeah, and the root cause it seems to be is kind of ABI compatibility related. Yeah, anyway, so I mean that is still also an ongoing problem. It's like a bug basically. So I use basically like you can use like the clang compiler, just anything, clang plus plus compiler to uh, get so you get a dot. It's not compiling it to an executable. It's a like library. I'll like compile it to a .ll file, which is like this is LLVM IR basically in the LLVM language form, and then I can use in like LLVM. I think there's LLVM AS. I'm not sure exactly what it's called. I think it's called LLVM AS, LLVM assembler. I'm not sure, something like this, which then converts these files into .bitcode. So I'm using these for now. I don't know, like this is like this did I was like experimenting with this. I don't think this is like some standard to do. I don't know. Like usually people have like .lib files for libraries, um, for static libraries, or like in Windows like you have .dll files for like dynamically linked libraries. But I don't know. This was like something I was trying out this, and it does work actually. So you can have like these bitcode files, and then what I do is in this step, at this step when we are moving your modules to a shared context, you uh, take your bitcode file in the program, and you make a module out of it, and you just link this as well into the same context, and then you just have the thing. Or I think, wait, am I doing that at this stage, or I think yeah, I do it basically at this stage. It's just that it's like the code comes after this. So I first link all of these, and then I like link this whole thing. So basically, it's like the same thing. I think I'm doing it somewhere in here. Uh, um, so here, like yeah. So in this for loops, this is like the linking of all the files, and then for libs, I go through all the libraries that I need to link. I find them, and so get module from bitcode is like the thing that I said. It's taking the bitcode file and creating a module from that, and then I move that into this. Uh, okay, so yeah, this is the list. These are actually this is a list of modules, and yeah, at this stage I'm linking them. Yeah, so actually I was not saying anything. So actually I'm kind of not wrong. So this is a list. So I've not linked them yet. We link, so we get all our modules here, and then we link them here. So basically, it is like linking is happening at the same time. So you just create a list of all of these. So I just basically form a list of all of these things, and then I just link them into that context. Um, Actually, I mean, it's actually not wrong. So first you move them into a shared context and then you link them. So I kind of actually messed this up. Uh, this whole thing is not exactly linking. I mean, you could call this whole thing linking because you're moving it into a shared context for linking, but the actual linking happens. And this diagram is kind of wrong actually. It looks as if I'm linking them here, but actually first move them into a shared context, and that they're still they're independent modules, and then you link those modules after they're all in that shared context. But anyways, I mean, like, uh, I think it makes sense. Um, so anyways, at the end you get like one module which has everything, including libraries that you included in your program. And yeah, and then finally, like there is one step at the end, because at this point if you just directly do something for a target, you will just get a auto file like the in the same manner like you would have gotten from these, but actually we want a .exe. So there is one last stage to this, um, which feels annoying maybe considering like we have gone through all of this. uh, but yeah, that's like it's like one small last stage, and this stage is sort of, I think, this is kind of OS dependent, because here we need to like create the exe, and this kind of requires uh, some stuff which involves, I think, like OS related stuff, if you want to do it like in the program in a efficient manner. Like you could obviously just call like a you could just call an external linker, which is another program, and you can invoke that, and it will handle everything on its own. But then that whole syscall, I mean not syscall, that call of another program itself is going to be extra uh, overhead. I mean, it will just add a lot of slowness for no reason. You don't need to do that. We can handle linking in the program itself. And so I'm doing that, and it's kind of just being done here. So I'm doing that for Windows right now, if I remember. Yeah, it's a lot of stuff. Yeah, make executable from object. So broadly, the thing that's happening is here, running this. So what we need to really do is like we need to link against certain basic things, certain static libs. Um, so like okay, to kind of I think cover this. How do I put it? So there is okay, it's not white. When we write a program, we usually have like some entry point, like some main function. We'll have some main and like some maybe some something like int main, and we have something in this, and we call this the entry point. But actually, uh, this is not really the actual entry point per se, for the actual when you create an executable. Um, so for the operating system, there is something that is recognized as an entry point, um, and you need to actually specify that. Um, So if I'm not wrong, in Windows by default, I think there's like a win main. Um, like I think I'm not sure if this was it. Um, this win main is I think for GUI. If I'm not wrong. So this is for GUI applications, but for console applications, like there's main CRT startup. So um, and I think this is the one that we care about because the compiler is basically a console application. Um, and the way you get all of this is so you have your program. So we compiled this into something, and at the end of everything that we had some .o file. Let's say it's not actually like we didn't emit this file. We didn't create a file. We could create it, but okay, let's say yeah, we probably do create it. At least right now, I'm creating it. So we created a .o file, but we need to link some more stuff into this. Um, why we need to do that is first of all to know where the actual entry point is. So this is the actual entry point, and this comes from the C runtime library. So this is like the C runtime, and so this is kind of important. Uh, this brings with it like stuff related to like the entry point. So in a way it's like this whole thing is wrapped in this actual entry point. So the main CRT starter will internally like call main, and we have like so the stuff like people write in main like int argc, like you have like argc and argv. These actually get pushed into this over here in this function at the startup. So it pushes it into like the stack of the program. Then it calls that program, the main, and um, yeah, basically that's like the entry point related stuff. But the C runtime, so uh, and when we say C runtime, so we're linking against this is also like a library. So there's some libraries for this, like there's VC runtime .lib, um, and there is so there VC runtime. If I'm not sure, but so msvcrt .lib. So I believe like I think like msvcrt was older one, and now it's replaced by this. But I don't know. Like I think so for some reason like still both are linked. I guess sometimes, but right now I think I'm linking them both. I think yeah. So I'm linking both of these, and there's the UCRT, which is like I think Universal C or C runtime or something like that. Um, so these things are C runtime rated stuff. So the entry point and all is like one thing that is needed, but there's a lot of other stuff that comes in, which is like very basic. Um, so basically, if you think about it, like when we say like the C standard library, which has stuff like printf, um, there's like malloc and free, and all these things. Like even string related libraries, like you can have strcmp, um, strlen. So all of these are methods that are defined in certain standard libraries in the C language, but actually these are going to be there in like like these libraries bring in all of these things for you to use. So what that means is that you can actually use these in your own language, even if it's like your own custom language. It doesn't have to be C or C++. So in my language, I can, if I link these libraries, I can now use these uh, all these functions and even like there may be other symbols and stuff, uh, and like I can just basically use them now. So that's one advantage of like using the C standard library, like the CRT basically. Uh, like because it's actually this part is not strictly necessary, because you fundamentally just need to have a entry point. So you could actually bypass all of this. So if you just have your own like underscore start function which calls main somewhere, and like you maybe handle like the arguments and all RCRB, and you specify that this is the entry point when you're like linking into the executable, and the only thing you really need to link against then is like kernel 32. And at the beginning I was actually doing this. I had my own runtime. I have even, I think, kept it somewhere still. I think it is there somewhere. If I see include source bin runtime. So yeah, so this is a runtime I had written. So as you can see it here, main is defined, exit process. So main is being called from this. So we are literally calling main in this here, and underscore start is like the actual entry point of this program. And so earlier I was basically defining this to be like the entry point. So I think at slash entry I would have written underscore start and, over here, uh, and then basically I wasn't linking against all of these things. That wasn't needed then. Um, so you could do that and it would still create an executable, but you wouldn't get the advantage of all of these standard libraries that you can use, which is useful because I mean printf is actually not too difficult to implement, except that it requires like variadic args, which is kind of a pain. Variadic args is required because like in printf, uh, like you don't just have a string, you have like a %d and %f, like you might have multiple things, and then you need to define like where these are coming from. So you have some variable a that is going to be this integer, there's maybe some I don't know, some float which is this, and maybe even some %s somewhere which is some string. And so there could be many things. In fact, there could be an literally infinite number of possible. I mean, not literally infinite, but there's no actual limit to like how many things you can have. So printf as a function doesn't know how many arguments there could be. It literally just allows you to have the string, and then after that you can have like any number of characters. So actually, the function definition of printf is something like, I think it returns the C printf. I think it returns like an int. I don't know exactly, but let's say it's an int. It would probably be something like int printf. Int printf. This is like basically it's like, I think, const char star. Um, and after that it's literally just dot dot. And dot 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 is actually not, listen, I'm not writing it just like for no reason, like just to explain. It's literally part of the syntax of print. Like the definition itself has dot 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 in it. And like you can actually look into like the standard library. So if you go to stdio.h, which you can actually do, you can go to so these libraries are defined in Windows. It's you need to go to like the Visual Studio Build Tools, and there you can actually see your libraries. So I think like I can show it maybe even here. It's, I'm not exactly sure where it is. I forget it every time. Public, no. don't remember where app data is. Yeah, app data moving. Or is it local? Thing. Huh. Yeah, this is. I can just check it from my own code. Um, Visual Studio, Path, Windows, SDK, Get. Okay. Program. Oh, program files. Studio. Yeah. PC tools, MSVC, and I think in include. So here these are all the C standard library header files, and here you should be able to see stdio.h. Mm, I think I can search it. This what's that? So CRT. These are the libs. Okay, anyways, even CSTDIO should have something. Uh, I mean, okay, so this is including STDI. So that was not interesting, but anyways, so that's not relevant. But yeah, the point was that you can like look into it and you will see like would have defined like this in this manner. But yeah, so printf is one thing. Then there's like malloc, there's free, and all these functions. So like malloc is important because you need to when you're allocating. So normally when you just like define variables or things like that, you're allocating memory to the stack, which is like stack based, and it's happening by the program itself, but maybe you want to like dynamically allocate memory, and for that you need to like use something like malloc. Even though malloc itself has like it's not like the most efficient way to do it, but it's like just the like one of the most basic things you use. So and then there are obviously like things like these string related operations. Again, you can write these yourself, but it's just a matter of like how much effort you want to take on your own. If you're like implementing like a real professional grade language, uh, even there like it could depend on you whether you want to like have your own libraries like from scratch. But yeah, it's just like if you are like writing a compiler and you want to start using the language for some basic stuff, it just becomes very easy, and it's like kind of fun to play with, because then you have like all of this stuff that you can use, and you can start doing things that are kind of rare. uh, because also like it allows you to like work within like Windows APIs, or and a bunch of like things that are going to assume that you have these things which are part of the C runtime, and then like you can just uh, use your language as if it's like kind of almost fully functioning. So yeah, it's just convenient. Um, so that's like the kind of the last stage, pretty much in the process, that you just generate that executable, um, which I think I had shown. Yeah, make executable from the auto, and just all this code is basically needed only to get the paths to all of those libraries, kernel 32, UCRT, um, and all of this stuff. Uh, and This is a little bit annoying, but it's like just getting paths from some location, and it's also like here I'm like caching those paths once you get them the first time, so it doesn't have to calculate them again and again. But yeah, that's basically what it is, and the actual cost of running basically just happens at this place, create process A, um, which actually calls that it calls like the LLD linker. So here I'm using like at this last step, so I'm not writing my own linker for this. So this is using the like the LLD linker, which is I think part of LLVM, and then like where you can use maybe um, there are other linkers also, but yeah, I mean, like I was checking like the RAT debugger that I think Ryan Flurry and at Epic Games, and they have created that debugger, and recently it sounds pretty nice, and they have their own linker also. I don't remember the exact name. I think it was like the RAD linker or something, and I think it was maybe like slightly faster when I compared it for like just a very small program compared to LLD. But yeah, right now I didn't replace it because I mean that was not. I don't know. Maybe I might have to like check it for some more serious benchmarks. Like I don't know actually how much difference it will make, and I mean it's like just one small part of this process. Uh, but yeah, I mean, uh, so broadly that's pretty much I think everything that we have covered. Um, and So yeah, as for like this last thing that I wrote, it's just uh, so this is just a side project that I worked on just for fun, and as as for a side project, I have like worked on it for a very long time. This is like when I say side project, I don't know what it's supposed to mean. I just do it for fun, little like people play video games. I think that's I just like there's no reason for me to do it. I could do anything else, but and sometimes I do other things because I get bored. Like you, like if I had to like just do this as a full time job, maybe I would get bored. I don't know, maybe, but I just happened to spend a lot of time and come up this far. I think if I had even maybe known how difficult like things like using LLVM would be, or like how irritating like the linking stages, then I would have probably not even started making this whole thing, because like literally like each one of these is like a huge amount of effort. Not I think not a huge amount of effort. Like the Lexer, I think it took me like 2 or 3 days to write the first time. Pass also, I think I wrote like a week later. I was done with the basic parser. But yeah, I think these were very irritating. Um, but yeah, I think, but I'm kind of very happy that I did this. It was useful to know. As for features, like it's a language, so if I go to, I have, so I have like this. I I began to realize that like there are like lots of language related things that I'm adding, so I need to keep track of it even for myself. And I'm not that interested in like documentation, like in a serious kind of documentation, because this is just a side project. But I had to have something, so I kind of made use of. I just I used like some on I went to VS Code and opened like Copilot and like I created like a basic template, and then I modified that, and I came up with some basic sort of a specification basically. Let me remember. I think it's just slash. Yeah. So this is a like the page I have. I wanted it to be like this raw HTML like page because I just don't like CSS. So yeah, I think this looks nice, and it pretty much covers like most of what I have. I think implemented till now. Um, which this is like, as you can see, I think it's like basically just a subset of C, and I have like type devs, enums, and there's stuff that I need to add still. These things I added recently: switch case, type devs, enums. Like I fixed some bugs. Periodic args is buggy. It doesn't really work properly. And I mean, there are obviously probably many bugs in the whole thing. Uh, the, and there are many things that I have to do. So I have L values and R values that I mentioned somewhere in between. I'm not actually handling them properly right now, and that is when I was implementing pointers. So I'm not actually. I kind of have a basic implementation of pointers that I've written, but I got stuck at this point where I realized that I need to now actually look into some real way of keeping track of whether an AST expression is an L value expression or an R value expression. Because till now I was able to like hack my way through it, because I think what was happening was, if I have like some kind of something expression like this where something like a equals 2, um, I just assume that I will treat this as an L value expression, which means that when I'm going to translate this, this should be like a load two, 2 is supposed to be loaded into the address, uh, in this address location, which is like the pointer, like whatever address A is defined at. Um, and not the value of A basically. Like you obviously are assigning something to the address of A, not the value of A. You can't do that. So I just assume that, and I assume that this thing is going to be the value itself, um, and it looks like it's simple here, and you don't need to do anything else because it's just an equal to sign, and you know that this is this and this is this. But there are problems when you actually have like pointers, because if you have a pointer like int star p, you have defined this somewhere in your program, and now you have something like, I don't know, like you have p is equal to something, and you do this. Um, what was I saying? Oh, sorry. I think I should have done this on the other side. So right now, what I was doing is, yeah. So this, so before I go there, just like I could have another example like a is equal to something something plus b. So here b might be, internally like a pointer to the like the address like where this is. But then I want to actually use the value of b for this particular use case because this is supposed to be an r value expression. So I will kind of do something equivalent to a dereferencing thing, and I'll get the value of b and then I'll use that in this whole thing. And the way I do that is just see that I have like the pointer, like the address to this thing, and not the value. But that is kind of a hack because I might actually have a pointer itself, and if I have something like a is equal to something something plus p, I don't actually want the value of p to be dereferenced because p itself is of a pointer type. So I don't want to like dereference this and get the value of something else. I literally want to add the value. The value itself is the address in this case, and I want to add that and return it. So just because it's a pointer type internally somewhere, you can't just use that as a hack to dereference things. So that was a bug right now in my like, pointer implementation. Um so I need to actually like keep track of something, whether it's an L value or an R value. I don't know if this whole thing made sense. Like I was like, trying to kind of describe the problem that is occurring in the code without mentioning the code. But yeah, so there's like stuff like this, and I want to like there are many features I mentioned that I need to do. Structs are like a big thing. I want to have like range based for loops, like for item in items, that kind of a thing, which is like in Python, C++, you would have all that. Um, there's like RC, RV, which I'm not having. All of this actually needs to be done, but for this all I need kind of to implement pointers first because that's just like very basic, and it's going to like make a lot of things possible later on. Like RB is kind of a pointer type, so I need pointers. And then I mentioned memory mapping for the Lexer, which I'm not doing. I need to do that. And error messages, that to have multiple error messages, I am like just displaying one error message and then I like stop the execution. But that's also not correct. So I kind of did this partially. So there are actually a few things I've done partially. I've done this partially and the pointer thing partially, but I stopped and I just left it in between. That's remaining. So yeah, I think there's a lot of stuff to do. I don't know how much I'll work on all of this. This is because, as I said, it's just a side project, and it's. I mean, it's done pretty, I think, extensively just for a side project, but it's also not. So it's like big for someone who just does like a thing like randomly for fun, but it's for a compiler. It's actually like very small. This is like very elementary as a compiler. So, but it's not bad. I think it's okay. Um, so yeah, I think that's I think good enough for today. I pretty much covered a lot of stuff. So yeah, let's see what else later on I'll do. If I continue working on more stuff, yeah, I think that's good for now. Okay.